OK, next up is a paper on predicting IPv4 services across all ports. This paper will be presented by Liz Izhikovic. Liz is a fifth-year PhD fellow at Stanford University, advised by Zakir Durumich. And Liz will be on the job market for faculty positions in the fall of 2023. So pay attention. Go ahead, Liz.
Thank you very much. OK, so let's talk about predicting IPv4 services across all ports. Internet-wide scanning has been used in hundreds of studies, from understanding the topology of the internet to measuring the security of the internet. However, no study has actually analyzed the entire IPv4 service space. And this is because the IPv4 service search space is simply too large to do so. If we were to scan all 65,000 ports across all 3.7 billion public IPv4 addresses, that would take roughly 5.5 years if we were to use one of the fastest internet-wide scanners, ZMAP, at 1 gigabit a second, which is a safe, non-overwhelming bandwidth. So to combat this problem, nobody wants to scan for 5.5 years, studies have done generally one of two solutions. First, studies will only scan assigned ports, or ports that are relevant to their research study. So if one is studying Telnet, they might choose to scan all of port 23 and or port 2323. Alternatively, studies may also only scan the most populated ports. So they may choose to scan port 80, 443, all of these ports that we're quite familiar with. However, by taking one of those two approaches, researchers are actually unintentionally missing billions of IPv4 services that are actually live. So our same team actually last year at Usenix Security showed that the majority of services do not actually run on their assigned ports or do not actually run on popular ports. So if one were to scan the top 5,000 ports, they would miss an estimated 1.9 billion, or the majority of all services on the internet. And moreover, services on uncommon ports are actually not well represented by services on the common ports. So for example, uncommon services are more likely to be less secure. And so by only studying the popular services, we actually have a very biased view of the internet. So in this talk, I'm going to present the first scalable and wall-time efficient solution for predicting IPv4 services across all ports. And we call this system GPS. GPS's algorithm works in roughly 4 parts. First, GPS collects a seed set. So this is generally an IPv4 sample across all ports, and it uses this seed set to learn from. Second, GPS is going to construct a probabilistic model for service prediction. Third, GPS is going to use the model to predict at least one service across all likely responsive IPv4 hosts. And we're going to get into detail of why it chooses to just predict one service first. Finally, GPS will use the model and that first found service to predict all remaining services on responsive IPv4 hosts. OK. First step is collecting a seed set. So GPS starts with zero knowledge about the internet, and it has to learn about service patterns from somewhere. So this seed set generally consists of IPv4 services, perhaps a 1% sample of the IP address space that we've scanned across all ports that we want to predict. So in this case, all 65,000 ports. And in this seed set, we might find, for example, here, a Cisco box. And because we've scanned all 65,000 ports, we found an obvious login page on port 80, but also an HTTPS application on this slightly weirder port 60443. In the second step, GPS is going to use conditional probabilities to find the most predictive feature values. So in our seed set, we've likely found a bunch of these Cisco boxes along with other hosts, and we've probably found that some of them respond on multiple ports and others on just one. And so using this entire seed set, GPS is going to start calculating, OK, given that a host responds on port 80, what is the probability that it also responds on port 60443? And it's also going to use network layer features and application layer features as well. So given that the Cisco box hosts a login page on port 80, does it increase or decrease the probability that it's going to respond on the other port? And so more concretely, GPS is going to model these 4 correspondences, and they're all going to use one or more of the transport layer, network layer, and application layer features. So why are we even using conditional probabilities? There are a lot of predictive frameworks out there. First is conditional probabilities are accurate. Math surprisingly works. Second, these conditional probabilities are actually simple and parallelizable computations that we can do across all 65,000 ports. And this is going to become important. Third, conditional probabilities require minimal training data. So unlike machine learning algorithms, which generally need millions of data points to train on, GPS can actually successfully predict services with just 2 IP samples per port, because it's a probability at the end of the day. On the flip side, it is computationally expensive to brute force all of the correspondences that I've showed you to calculate the probability of all possible combinations of features and how predictive they are, but we're going to mitigate that later in this talk. OK, so we have these conditional probabilities, but there becomes this problem. How does GPS obtain a priori information about a host? So these probabilities actually assume that we know at least one service, or there's at least one open port on the host. But in the seed set that we fed into GPS, we've only given it information about maybe 1% of the internet. And so it really doesn't know anything about the other 99% of hosts. And without this model, actually the only information we do have about the 99% of hosts is a network layer feature, so the actual IP address itself and maybe the autonomous system it belongs to. So to help GPS actually obtain this prior information, the solution we've developed is GPS is going to collect a minimum amount of the most predictive information about every likely responsive host. And it's going to minimize this because this is a very expensive step. And I'm going to show you in the next slide an example. So in this third step, we've collected all of these Cisco boxes and all of these hosts. And as it turns out, if you look at the entire internet, the probability of a host that responds on port 60443, it actually has a 71% chance of also responding on port 80. And this is because it's a very specific class of devices on the internet that actually respond on this weird port. And the majority of them do hold a login page on the common port. Now, the reverse is not true on the internet. So only 0.2% of devices that respond on port 80 also respond on this weird port. And this isn't surprising. We know that a lot of devices respond on port 80. We don't expect them to respond on the other port. And so the insight here is that port 60443 service is more predictive and more helpful to know of another service. And so it makes more sense for GPS to search for port 60443 first so we can successfully use it in the final predictions. And so the algorithm that GPS is going to execute is, for every IP and host that it finds in the seed set, it's going to compute all 4 of the probabilistic models using all the services features. And then it's going to identify that prior port that results in the maximum final probability. And it is going to save that port and the network of the IP address in the seed set to scan. So we're going to come up with this prior scan list. GPS is then going to scan all these IP addresses on these ports. And we're hopefully going to start finding other Cisco boxes in that 99% of the rest of the internet which respond on these kind of strange ports. And in the last step, what GPS is going to do is it's going to take the result of that prior scan. It's going to take the result of all the probabilities that it's already pre-computed in the past, and it's going to apply both. So in this case, for all the addresses that respond on port 60443, there's a 71% chance they'll also respond on port 80. So GPS is going to save that information. And it's going to order this predictions list in a descending order of most probable predictions. So at the beginning, GPS is going to be scanning really fast and really accurately because it's going to go through the most probable predictions, and the performance will slowly degrade. So the algorithm's summary is we started with the seed set. It then computes all the conditional probabilities. We use that to find the first service across all hosts. And then we combine the model with that first service to predict the rest of the internet. Now, as I mentioned before, this second step is computationally and memory expensive. But it is parallelizable. And so we're going to implement GPS with serverless compute in order to mitigate the expensive nature of this. So serverless computing, in general, provides an elastic and parallelizable computational environment, which generally minimizes wall clock time of an operation. And so we choose to implement GPS with Google BigQuery, which is a serverless database platform. And implementing GPS in a database query language, interestingly enough, makes the reading, aggregating, and joining among shared fields, so in this case, the services features, very intuitive and fast. OK, let's evaluate GPS. So one of GPS's metrics for success, or one of its objectives, is to maximize finding services across all of the ports. And so we're going to evaluate that by calculating the fraction of services. So this is, we're going to divide the number of services that the system, GPS, has found over the number of services that are present in some notion of ground truth. Now, evaluating against a ground truth presents a bit of a problem, because no method exists to efficiently scan all IPv4 services across all ports, and we didn't want to wait 5.5 years to evaluate GPS. So for the purpose of this talk and the paper, we approximate the ground truth, and in this case, we're going to use 100% IPv4 scans across the most popular 2,000 ports. So how well does GPS perform? Well, its predictions find 99% of services, IPv4 services, in less than 24 hours. Much better than 5.5 years. So on the x-axis, we see the amount of bandwidth that GPS needs, and on the y-axis, it's this fraction of service metric. And so we see, at the very beginning, GPS finds 94% of services really fast. And this is because, again, it's going for those easy predictions. And then as the predictions start getting worse and worse, but still much better than random, of course, GPS needs more and more bandwidth to find that long tail of services. We also evaluate GPS against a machine learning implementation. So prior work used an XGBoost classifier to predict services on a target port. Now, what we found about their classifier and machine learning systems in general is, again, they need a lot of training data. And so this specific implementation needed 10 million training IPs per port, which 99.9% of ports actually do not even have that many IP addresses responding on them in the first place. But for the ports that their system works on, we evaluate GPS on as well. So we find that GPS saves up to 28 times more bandwidth than this machine learning implementation when scanning the majority of popular ports. So on the x-axis, we see there's a list of common ports we're all familiar with, and the y-axis is the bandwidth. And so we see that GPS nearly always outperforms machine learning. So GPS's time complexity. Well, using a single core, so GPS needs to calculate the predictions, and it takes 9 days and 9 hours if we were to brute force all the probabilities on that core. Interestingly enough, this is still 5.5 times faster than if we were to attempt to use the machine learning implementation across all 65,000 ports. However, when we use serverless compute, so we actually throw in GPS's algorithm into Google BigQuery, GPS calculates predictions in 13 minutes. So this is 10,000 times faster than the machine learning implementation, and this only costs the user 75 cents. So GPS's bottleneck becomes the bandwidth. The seed scan collection can take a while because there's no smart way to collect the seed, and as a result, that can take days or months depending upon the size. And the uploading and downloading of data can also take hours between whichever serverless platform you choose. However, with an available seed scan, which our lab is publishing for the community to use, GPS finds 99% of services from beginning to end with the total runtime of less than 48 hours. Again, much better than 5.5 years. So in conclusion, GPS is a scanning system that we've built that predicts IPv4 services across all ports and finds the billions of previously hidden services that researchers have not studied. To predict services, GPS parallelizes conditional probability calculations, and GPS can calculate all the predictions in 13 minutes when using serverless compute. GPS finds 99% of services in less than 48 hours. And we've open sourced GPS, so it's available to use for anyone in the community right now. Thank you.
Questions? Yeah, here.
Okay, I need to walk there, maybe.
Yeah, go ahead.
Hello?
Yep.
So my question is, are you combining GPS with ZMap to actually do the scanning, or is it just prediction and then you stop there?
Yeah, so part of the GPS pipeline when we implement it is we use a couple of internet scanning tools, including ZMap, lasers. So you need some tool that's actually sending the packets, and GPS is the predictive framework that works on top of it.
And did you do any work to kind of verify, did you find all ports, or how much percentage of the ports were found using this mechanism? Were there anything missed? Is that work also did, or is it authoritatively find everything based on this algorithm that kind of keeps working?
Wait, could you repeat the question? Sorry.
Does it find all known ports, or is there a probability of missing something? Is that something that you calculated, or was that part?
Yeah. So we thoroughly evaluate across all 65,000 ports in the paper, and we find that just like with any prediction system, it's going to perform really well on the predictable hosts. And then, if one person makes a random configuration decision, then it's that long tail that becomes more expensive to find.
It becomes more expensive, but do you find it, or is that
if you give me unlimited bandwidth in 5.5 years, we find it.
Of course.
But so yeah, it's a trade-off, and this is a trade-off that actually any predictive system is going to face. And we kind of discussed the limitations of this in the paper as well.
Yeah, great talk and super interesting results. I'm wondering, since your system is mainly limited by scanning bandwidth and the time it takes to upload into something like BigQuery, have you considered actually just running the scanners from the cloud? Is that possible? And then, what are the trade-offs for just hosting the scanner, let's say, on VMs right next to BigQuery?
Yeah. So the amount, you're generally not going to get that much bandwidth from the cloud. You're actually going to start denial of servicing the cloud operators if you try to run this from Amazon or Google. Now, you may kind of set up a separate contract with them, but if you're just a regular user and you want to run from the cloud, you're actually severely limited by the amount of bandwidth. And so generally when we do these studies, we do it from our own lab, and we have our own egress point, and it's a very special setup.
Any more questions? Yes, go ahead.
Nitendra from Technical University of Munich. Great talk, first of all. So did I read it right that your evaluation uses 2,000 hosts?
So the one that I presented here is 2,000 ports. We also have one on 65,000 ports. The trade-off, though, is as we evaluate against more ports, we have to subsample the IP addresses that we've exhaustively scanned on those ports.
And do you know how many hosts were you scanning?
The number of hosts that we found?
Yeah, so total number of hosts, yeah, exactly.
Yeah. So in the paper, we predicted roughly, so we had 28 billion predictions, and we found roughly like 400, 500 million-ish hosts. So it's still less than 1 billion, I believe, in terms of the amount of active services that are out there.
Okay, cool. Thank you.
Okay. Let's thank the speaker.